Welcome to Elimu Live. I'm Mr. Byron, and our topic today in chemistry will be nitrogen and its compound. So today we are going to talk about nitrogen and its compounds. So this will be our topic of study today. We are going to focus on nitrogen and its compound, talking about preparation of nitrogen, preparation of its compound, its oxides, their chemical and physical properties, and also the equations that are involved under the topic. So let's begin. Due to time, let's just cut to the chase. So nitrogen, it's an element with atomic number 12, or not 12 but 7. So the relative atomic number of nitrogen is 7. So it is element number 7 on the periodic table, giving it an electronic configuration of 2,5, meaning that it belongs to group 5. So nitrogen belongs to group 5 and period 2. Yeah, it's an element with atomic number 7 on a periodic table. So its electronic configuration is 2,5, placing it at group 5 and period 2. So I know you all know how to place an element in its group and periodic table by considering its electronic configuration. Now, nitrogen, it exists as a gas, a diatomic gas in the air, yeah, and it occupies 78% of air. So it means for every 100 volume of air, 78% of it is nitrogen. So that simply makes air the main or the major source of nitrogen for the industrial uses. So today we shall be talking about how do you obtain nitrogen. How do you obtain nitrogen, both from air and how do you prepare it at laboratory level? So remember, like I said, in air, nitrogen occupies 78%. So that makes it the major source of nitrogen, making the air the major source or the major source of nitrogen for the industrial uses. So all the industrial uses involving manufacture of nitrogen compounds like ammonium and nitric acid, we obtain nitrogen from air because that's where we can obtain it in large quantities. So we shall be talking about how do you obtain nitrogen in air and how do you prepare nitrogen at the laboratory level. So let's begin. Sorry for that. So preparation of nitrogen. So nitrogen can be obtained from air, and also nitrogen can be prepared in the laboratory. So we are going to talk about both the methods. How do you obtain nitrogen from air and how do you obtain nitrogen at the laboratory level? So the first method is isolation of nitrogen from air. We're going to talk about isolation of nitrogen from air. Now, under isolation of nitrogen from air, I want you to note that air is just whatever we see, which surrounds us. Now we want to obtain nitrogen from this air. And remember, air, it comprises other mixtures. Like air, it comprises of, we have dust particles. Air also comprises of water vapor. Also in air, we have inert gases. And the major part of the inert gases, it's argon. And also the same air, it has carbon 4 oxide. We have carbon 4 oxide in air. We also have oxygen in air. And also air is made up of nitrogen. Now, we want to obtain nitrogen from air. And the method of obtaining nitrogen from air at large scale is what we call fractional distillation. So nitrogen is obtained from air through fractional distillation of liquid air. So first, remember, air is gaseous state. So because it's fractional distillation of liquid air, we have to convert this nitrogen or this air into liquid state, the gaseous state into liquid state, so that you can carry out fractional distillation. And also remember, our main point of focus is nitrogen. That's what we want to obtain. But when you check at air, it also comprises of other elements. We have dust particles, it have water vapor, argon, carbon dioxide, oxygen, and nitrogen. That means that if we want to obtain nitrogen by fractional distillation, the first step does not become just fractional distillation. We also have to make sure that we eliminate the other elements that are also compressed in air, which are unnecessary in this process. So let's talk about fractional distillation of liquefied air. So under fractional distillation of liquefied air, keep in mind that our main point of focus, we want to obtain nitrogen. Now, we have to eliminate the dust particles, water vapor, and carbon dioxide. How do we do that? So let's begin. So this is air. We want to obtain nitrogen. First, we pass this air into filters. Here we have our filters. Now, our filters here, they remove dust particles because dust particles are removed by the filters. So any dust particles, solid particles that are in air are removed by the filters through the method we call electrostatic precipitation. So in examination, they will ask you, identify the process taking place at this place in filters. So the process is electrostatic precipitation because the filters used to remove dust particles, in this case, they are not just the normal filters. They are charged filters with charges. They are electrostatic precipitators. So they remove these dust particles by the process of electrostatic precipitation. So here we have our dust-free air. This is dust-free air. We have removed dust in the filters. So we have eliminated dust particles. Now we are remaining with water vapor and carbon dioxide, which are also unnecessary in this process. We don't want them, we want to eliminate them. So let's remove carbon dioxide. How do we remove carbon dioxide? To remove carbon dioxide, we simply bubble or repass this air through concentrated potassium hydroxide or concentrated sodium hydroxide. So where concentrated potassium hydroxide can be used, also sodium hydroxide can also be used. So by passing this air into these concentrated solutions, either potassium hydroxide or sodium hydroxide, we eliminate carbon dioxide. So carbon dioxide will react with the potassium hydroxide to form potassium carbonate, which will be pulled out as solid because carbonates are insoluble. Okay, so this is carbon dioxide free or removed. So it is removed here. So carbon dioxide free air. So this air coming out from this chamber is free from carbon dioxide. Now, after removing carbon dioxide, now our main point of focus is now to eliminate water vapor. How do we eliminate water vapor and why do we eliminate water vapor? Now, first, we eliminated carbon dioxide because whatever we want to obtain here is nitrogen. And in the process of obtaining nitrogen by fractional distillation, we don't only obtain nitrogen, but we obtain nitrogen, oxygen, and argon. And now, the main reason why we are removing water, I'll tell you in the next few seconds. So here, we remove water by freezing or cooling it at negative 25 degrees Celsius. So water cools at 0 degrees Celsius. So if we cool this air at negative 25 degrees Celsius, we will be certain that we have eliminated all water vapor in that. If there's any water vapor, it will condense and then it will form solid and then you shall have removed it. Now, after there, we compress the arrow points this direction, and remember here now this air is free from water vapor. The air here is free from water vapor, and I'll be telling you very soon why we remove water vapor. So here we compress this air, compress at 200 atmospheres. That's the pressure, so we compress it at a very high pressure. The reason why we compress this air at 200 atmospheres is simply to keep it in liquids. Negative 200 atmospheres, we now cool it at negative 200 degrees Celsius. First, we compress it at 200 atmospheric pressures or atmospheres at a pressure of 200, and then we cool it at negative 200. Now remember, our air here, initially it was in gaseous state, but now we have removed dust particles, and then we have eliminated carbon dioxide. We have removed water vapor, and now we compress it. After compressing it, it becomes into liquid state, and also we cool it at negative 200 degrees. So remember, the state of this air at this point, it is in liquid state. So now we can carry out our fractional distillation. So it's at this point we carry out fractional distillation. So when we carry out fractional distillation, we are heating this mixture. And remember, we have eliminated water vapor, dust particles, and carbon dioxide. So our mixture here, the air, this solution that is remaining here, this liquefied air, it comprises of argon, oxygen, and nitrogen. And these three, each of them have a different boiling point. And at this point now, they are in liquid state, they are in liquid state. So when we start heating them to boiling point, we shall obtain them according to their boiling point. The one with the lowest boiling point will come out the first. So because it's at negative 200 degrees, so when you start heating it, the temperature begins to rise. So when it reaches negative 106 degrees Celsius, we obtain nitrogen gas. At negative 186 degrees Celsius, we obtain argon. And then at negative 183 degrees Celsius, we shall obtain oxygen gas. So you need to understand this procedure of fractional distillation of liquefied air, because in examination you will find a flowchart in this manner, but some of the boxes or some of the stages will be missing some information. For example, here they will indicate that this box is empty, but here they will indicate to you that now the air here is carbon dioxide free, and you will be required to identify the substance which have been used at this stage to remove carbon dioxide. So you should know that to remove carbon dioxide or to absorb carbon dioxide from air, we use concentrated potassium or sodium hydroxide. Now, like we said, at the filters, the method we use here is at filters. The method we use here to remove dust particles from air at the filters is electrostatic precipitation. Removal of carbon dioxide from air is through absorption, because we are absorbing it from air. And then freezing here, it's simply freezing. That's the method that we use here. We are just freezing it. And then here, it is fractional distillation. Now, our main point of concern is nitrogen. Even though you have obtained argon and oxygen, but we have also obtained nitrogen, because this is what you are interested in, to obtain nitrogen gas. And also in examination, you will find that these elements are missing here. They will want you to identify gas X, gas Y, and gas Z. Now, for you to identify gas X, Y, and Z, you should know which gas boils at what temperature. From this diagram, nitrogen is obtained at negative 196 degrees Celsius, argon is obtained at negative 186 degrees Celsius, and oxygen, we obtain it at negative 183 degrees Celsius. So with this method, we are now able to obtain nitrogen gas in large quantities necessary to be used for industrial processes like manufacture of ammonium in the Haber process, which I'll be talking about in the next few minutes. Okay, so this is the method number one, which is the industrial method, or which is the fractional distillation, and it's industrial method because we can't carry out at the laboratory level. We cannot carry out this process at laboratory level. So it is applied in the industrial method where nitrogen is required in large quantities. But in laboratory level, we can also prepare nitrogen gas. So you just allow me to delete this so that now we can talk about how can we prepare nitrogen gas at the laboratory level. Okay. So this is our setup that I'm doing here. This is our setup. This will be our setup. This is a stand. This is the setup that demonstrates how we can obtain nitrogen at the laboratory level. And from the setup, you can also tell that one of the chemical properties of nitrogen is that it's slightly soluble in water, because according to this setup, the method we are using to collect nitrogen gas here, it is a over water method. So this is water, this is water, you know, this over water method. This is a beehive, and this is our volumetric flask or round bottom flask. So in preparation of any gas, apart from nitrogen, nitrogen 4, nitrogen 1, nitrogen 2, and any other gas studied at the high school level, one thing you need to focus or need to understand is the method of preparation the reagents used, the equation, and also the method of collection. That's very important because that's the areas where they test. The reagents, equation, and the method of collection. Now, to obtain nitrogen gas in air, we simply react here. It's a mixture of sodium nitrate, that's sodium nitrate, and ammonium chloride. So we react sodium nitrate and ammonium chloride. I want you to underline this. This is sodium nitrite, not sodium nitrate. That's why it has a subscript 2. It's 2 here, meaning it's sodium nitrite and not sodium nitrate. If it was sodium nitrate, it will be Na, that's sodium, and then NO3. But this is sodium nitrite. Now, also here, we have a source of heat. We have a source of heat to decompose the product formed here so that we can produce or we can obtain our nitrogen gas. Now, when sodium nitrate reacts with ammonium chloride, this is the equation. Sodium nitrate reacting with ammonium chloride. What do you obtain? We obtain ammonium nitrite. This is ammonium nitrate and sodium chloride. Now, this ammonium nitrate, it undergoes thermal decomposition to produce nitrogen gas and water. This is ammonium nitrate here, undergoing thermal decomposition to produce nitrogen gas and water. So this is gas. Let's try to balance this equation. Nitrogen, you have them 2 here. It's 2, the other on the product side. Hydrogen, you have 4 molecules, 2 here. So we balance with 2. Oxygen, there are 2 molecules, 2 molecules. So it's balanced. So I want you to note the reagents. The reagents are very important. 1, to prepare nitrogen gas, we use sodium nitrite and ammonium chloride. Now, in examination, they will indicate here that we have a gas here. It will be identified as gas X. And this will be sodium nitrate and ammonium chloride. Now they will want you to identify which gas is that. That means that you should be able to write an equation so that you can come out to the products being formed. Because you cannot identify the product if you don't know how to write the equation. And it must be a well-balanced chemical equation. So, according to the equation, sodium nitrite reacts with ammonium chloride to obtain ammonium nitrite and sodium chloride. And then this ammonium nitrite, it undergoes thermal decomposition to give us nitrogen gas and water. Now, this nitrogen gas, we collect it using overwater method. That means that the one physical property of nitrogen gas is that it is slightly soluble in water. Good, slightly soluble in water. Also, I want you to note that the nitrogen is a reactive, and also it's very unreactive. It's unreactive because of the bond, the triple bond that connects nitrogen molecules. So it's very unreactive. So it requires a very high temperature to break it down because of this triple bond. And also, it's neutral gas. That means they can also show you that it can have a nitrogen gas here, this water, nitrogen gas being bubbled in. And then we have a red litmus paper, and you can have a blue litmus paper here. And they ask you for the observation. Now, they are testing if you know that nitrogen gas is neutral, meaning red litmus paper, whether it is wet in nitrogen gas, it will remain red, and the blue litmus paper will remain blue. Now, without wastage of time, let's talk about the oxides of nitrogen. Oxides of nitrogen, but don't forget about the reagents used to prepare nitrogen here, because there's some correlations between the reagents used to prepare nitrogen here and the reagents used to prepare its oxides, especially for nitrogen 1, which are going to talk in the next subtopic here. Good. So let's talk about oxides of nitrogen. Nitrogen has 3 oxides. We have nitrogen 1 oxide, we have nitrogen 2 oxide, and then we have nitrogen 4. Now, the reason it's called nitrogen 1, it's because the oxidation number of nitrogen in this compound is 1, because if we have a nitrogen unknown, and then we have oxygen here, of course, which is -2. So oxidation number of oxygen here is -2. And you know that oxidation number of a compound with no charge, it is 0. So that gives us 2x giving equal to +2 divided by 2 by 2. So x being the oxidation number of nitrogen will become +1. So the oxidation number of nitrogen is +1. That's why you call it nitrogen 1. Similar to this, oxidation number of nitrogen here is 2. That's why you call it nitrogen 2, and this one nitrogen 4. Now, I'll just cite here aside, during preparation of nitrogen, we said that we use sodium nitrite and ammonium chloride. And these two, they obtain ammonium nitrite. So underline this. To prepare nitrogen gas, we heat ammonium nitrite. And now, let's talk about preparation of nitrogen 1 oxide. To prepare nitrogen 1 oxide, what are the reagents? This is the similarity or the correlation between nitrogen 1 and nitrogen gas. To obtain nitrogen 1 oxide, simply, this is the setup. This is the setup, just similar to the other one. Similar to the other one. The method of collection is just the same. But now I want you to note the differences and the similarities. The reagent we use here to obtain nitrogen 1 oxide is ammonium nitrate. We use ammonium nitrate. Unlike in nitrogen gas, where we used ammonium nitrite, in nitrogen 1, we are using ammonium nitrate. Now, when ammonium nitrate undergoes thermal decomposition, it will give us nitrogen 1 oxide and water. Let's balance the equation. We have two molecules, hydrogen is 4, oxygen are 3, so it's balanced. So this ammonium nitrate. So for ammonium nitrite, it was for nitrogen gas, but in preparation of nitrogen 1, we use ammonium nitrate. So when ammonium nitrate undergoes thermal decomposition, we obtain nitrogen 1. Now, another difference is this. Even though all the gases are prepared, are collected using overwater method, but here, for nitrogen 1 oxide, which is being obtained here, we use warm water. The reason why we use warm water is because nitrogen 1 oxide is fairly soluble in cold water, and that means that if we dissolve it, or if we pass it over cold water, a large or a reasonable quantity of it will be lost through dissolving in that cold water. So we use warm water because nitrogen 1 oxide is not soluble in warm water. So if you see in any diagram in examination, there's warm water being used as a method of collection, just remember that it's nitrogen 1 oxide because that's the only gas actually we study here which we collect using warm water. So the reagent is ammonium nitrate, and it's very confusing if you are not well conversant with this concept. In examination, you'll find that we have been given ammonium nitrate, but because you recently read about ammonium nitrite, you will think that the gas being collected here is nitrogen. So don't confuse. If it's ammonium nitrate, we are collecting nitrogen 1 oxide gas. Now, this nitrogen 1 oxide gas, it is also unstable, even though it does not support combustion, but it lights a glowing splint. That's one of the properties that you should not forget. It lights a glowing splint. A glowing splint. It lights a glowing splint. So it relights a glowing splint. It has properties like those of oxygen. It lights glowing splint. So don't forget that. But it does not support combustion. However, you will be asked that burning magnesium proceeds to burn in nitrogen 1 oxide. Explain. Now remember, we said that nitrogen 1 oxide does not support combustion. But the question says that burning magnesium will proceed to burn in nitrogen 1 oxide. Why? It's because if you burn those heavy metals like magnesium, they produce a lot of heat. And now that heat, it decomposes this nitrogen 1 oxide into nitrogen and oxygen. That oxygen produced is the one that will facilitate that combustion, or it's the one that will keep that magnesium burning. So don't forget that. If you meet such a question, don't get confused. Nitrogen 1 is decomposed into nitrogen and oxygen. So that oxygen produced is the one that facilitates combustion, or the one that keeps magnesium burning. Now, this nitrogen 1 oxide, it's also a reducing oxygen. It's a reducing agent. Reducing agent means it reduces elements from compounds. Let's see an example here. It's an oxidizer. Oxidizer means an oxidizing agent. So we shall use an example. If we react copper with nitrogen 1 oxide, what do you obtain? When copper reacts with nitrogen 1 oxide, copper will reduce nitrogen 1 into nitrogen, and itself will be oxidized into copper 2 oxide. Now, I know you are asking yourself, why am I saying that copper is being oxidized into copper 2 oxide? Now, let's take out the oxidation number of copper here. The oxidation number of copper here, because it's an element, its oxidation number is 0. The oxidation number of nitrogen here, we just said it is 1. Oxidation number of nitrogen here is 1. Oxidation number of oxygen here, the oxidation number of oxygen here it is -2. That's the oxidation number of oxygen. Now here, oxidation number of nitrogen is 0. Oxidation number of copper here, because it's in a compound, it will be +2. And the oxidation number of oxygen here, because it's also in a compound, it will be -2 still. So you will identify that copper, the oxidation number of copper has increased from 0 to +2. That means that copper undergoes oxidation. Because its charge have increased from 0 to +2, we say that it has undergone oxidation. But the oxidation number of nitrogen has reduced from +1 to 0. So this one, it has undergone reduction. Nitrogen has undergone reduction. That's why I mean that nitrogen 1 oxide is an oxidizing agent, because it reduces copper to, it oxidizes copper to copper 2 oxide, and itself is reduced from nitrogen 1 oxide to nitrogen. So this one is oxidation. So nitrogen 1 here, it acts as an oxidizer. So that brings us to the uses of nitrogen 1 oxide. The first one, you just said that it's used as an oxidizer in rockets and also in car engines, because we have seen its oxidation properties. From this experiment, it has oxidized copper into nitrogen 1 oxide. So that brings us to this question. You can find this question in examination. You can have we have copper here. This is copper in a combustion tube. And here, let's say this is a question you can find in examination. This is nitrogen 1 oxide gas. Nitrogen 1 oxide gas is being passed over heated, this heated copper. So nitrogen 1 oxide is being passed over heated copper. And now they'll ask you to complete the diagram showing how the gas being obtained there will be collected. So you cannot get this question right, one, if you don't know to write the chemical equation taking place here. Remember, nitrogen 1 oxide is an oxidizing agent. So it will oxidize copper into copper 1 oxide, and itself will be reduced into nitrogen, meaning that the gas being obtained here is nitrogen gas. So you should know how to collect nitrogen gas. It's being collected by over water method. That will earn you 1 mark. Another question they'll ask you, of course, is why do you pass nitrogen 1 oxide first before heating begins? It's simply because to drive out air that was initially present in this apparatus. Because if we start or if we begin heating this copper before we pass through the apparatus nitrogen 1 oxide, copper will react with oxygen that is present in this apparatus to form copper 1 oxide. Remember that. So you can find that question. So according to these properties of nitrogen 1, we have said that 1, it is used as an oxidizer in a rocket and also in car engines, and also 2, because we have said that nitrogen 1 oxide is also relights a glowing splint. So it's used as an oxidizer, and it's also used as to produce flame in analytical works. Remember that. So those are among the major uses of nitrogen 1 oxide gas. It is used as to provide fuel, or used as to provide flames, or used as flame in analytical works, and also it's used to provide as an oxidizer in car engines and rockets. So without wasting our time, let's go to the second oxide of nitrogen, which is nitrogen 4 oxide. Now, for nitrogen gas, we said we heat ammonium nitrate. And for nitrogen 1 oxide, we said we are going to heat ammonium nitrate. That's just the similarity that I was talking about. So let's talk about nitrogen 2. We say that it is nitrogen 2 because the oxidation number of nitrogen in this compound is 2. Now, to prepare nitrogen 2, unlike the other nitrogen and nitrogen 1, here we react copper with dilute nitric acid. So you can have here nitric acid. This one will be dilute nitric acid. We are collecting here our dilute nitric acid. So we have dilute nitric acid and copper metal here. So we have copper and dilute nitric acid. So what are we going to obtain? We're going to obtain nitrogen 2 oxide. We obtain nitrogen 2 oxide, which is still collect using the over water method. And this is the equation when copper reacts with dilute nitric acid. So dilute nitric acid, because it's dilute, its chemical symbol will be aqueous to show that it's dilute. We obtain copper nitrate, which we call copper 2 nitrate, and then plus, and that's plus steam. So when we heat copper plus nitric, when we react copper and nitric acid, it will give us copper 2 nitrate plus steam, and then plus nitrogen 2 oxide gas. This is the equation. So this will give us a 3. Here we shall have here 8, because we have 3 of copper here, it will be 3. And then how many hydrogens do we have? We have 8 hydrogens. We have 2, so this will be 4. Yeah, and we have how many nitrogens? We have this one is 8 of nitrogen, and here we have 2 and 2. We have how many oxygens? 24 oxygens. This one are 6. 6 plus 4, that gives us 10. So 10, that's a difference of 14. This one will become 7. So that will be 7. So that's how you balance that equation. So when copper reacts with the dilute nitric acid, it gives us copper nitrate and steam and also nitrogen 2 oxide gas. Now, also note that to prepare nitrogen 4 oxide gas, we use dilute nitric acid and copper. Now, let's talk about nitrogen 4. How do we prepare nitrogen 4? Now, this is the similarity. To prepare nitrogen 4, we use concentrated instead of dilute. We use concentrated nitric acid. So when we react nitric acid with copper, it will give us copper and concentrated nitric acid, giving us copper nitrate and steam plus nitrogen 4 oxide gas. Now, when we react copper with dilute nitric acid, it will give you nitrogen 2. But when you react the same copper with concentrated nitric acid, which is liquid state here, then it will give you nitrogen 4 oxide. So this will give us 3 hydrogens. Yeah, there's 3 hydrogens. We shall balance that. Okay, so that gives us the equation. This will become 4. And this one will be 2. So we have 4 of nitrogen. We have 2. So we shall have 2 here. And the equation is balanced. Good. That's good. Okay. So also note that for nitrogen 4 oxide, we react concentrated nitric acid and copper. So this is Kong. So this is the similarities. You will go in examination and you will find a diagram, but it's incomplete. Maybe they will require you to complete the preparation of method and also to identify the reagents used. So that keep in mind that during preparation of nitrogen gas, we use ammonium nitrate, and the method of collection is over water. For nitrogen 1 oxide, the method of collection is over warm water. And for nitrogen 2, the method of collection is over water. And then for nitrogen 4 oxide, just like carbon 4 and sulfur 4 oxide, it's collected using downward delivery. So for this one, when using concentrated nitric acid reacting with the copper, the method of collection will not be over water, like it will be collected using downward delivery. And the downward delivery method, it looks like this. This is the downward delivery method. So nitrogen 4 oxide will be collected using downward delivery. So apart from these methods of preparing nitrogen 4 oxide, nitrogen 4 oxide can also be prepared by or through the thermal decompositions of the nitrates or those metals that are below on sodium in the reactivity series. So we all know the reactivity series. We have potassium, we have sodium here, we have calcium, magnesium, aluminium, zinc, iron, we have lead, we have mercury, we have silver, and then we have gold. So all those nitrates of elements below sodium downwards, if we heat them, if we put them under thermal decompositions, they will obtain what? We shall obtain nitrogen 4 oxide gas. I shall just give us one example. You will find that in examination situation, you have been given here a combustion tube, and at this point, we have silver nitrate. This one is silver nitrate. It's being heated. So they'll ask you also to identify the gas being produced here. We have gas X being produced here. Now, like I said, nitrogen 4 oxide gas can also be obtained by thermal decomposition of nitrates of elements that are below sodium in the reactivity series. Now, we have silver nitrate. So when silver nitrate undergoes thermal decomposition, if you want to score this correct, first you must know how to write the equation. Silver has a valency of 1, so this will just be 1. Silver has a valency of 1. So if this one undergoes thermal decomposition, it will give us silver and nitrogen 4 oxide, and then it also give us water or steam in gaseous state. So if silver nitrate undergoes thermal decomposition, it gives us silver plus nitrogen 4 oxide plus nitrogen 1 oxide. So by heating this, we shall obtain nitrogen 4 oxide gas. So if you are asked to complete the diagram to show how the gas X will be collected, first you must know which gas is that. It's nitrogen 4 oxide gas. So you know that nitrogen 4 oxide gas is being collected using downward delivery method. So you can now complete the diagram to show that it is being collected using downward delivery method. So don't miss that marks in examination. Also, they can also ask you to write the equation. If you're also asked to write the equation, you should be able to write the equation in chemical equation, and also balance it appropriately. We can also obtain nitrogen 4 by also thermal decomposition of zinc nitrate. So when we heat zinc nitrate, we shall obtain zinc oxide and nitrogen 4 oxide and water. Now, there's one thing I want you to note here. Whatever they ask here, or what they normally question here, or what they normally ask here, is about the color of this zinc oxide. So as a student, you should know the color of zinc oxide when hot and when cold. So zinc oxide when hot, it's yellow. It's yellow when hot, yellow when hot. This one will be very useful when answering paper 2 equations on a flowchart under metals, because metals can also be set under paper 2. And in most cases, you will find that we are heating a certain nitrate, and then we are obtaining a yellow solid when hot and white when cold. So zinc oxide is yellow when hot, and then it is white when cold. So if you find that in a flowchart, that there's a certain, let's say we have this is a solid X. We have solid X. Now this solid X is being heated, and then it's obtaining here a solid which is yellow when hot and white when cold. That means that the solid is zinc oxide. And also this solid, under heating, it also obtain a brown gas. We have a brown gas here. It obtains a brown gas here. Then it means that the brown gas is what? Nitrogen 4 oxide gas. So if someone asks you now, give the identity of solid X. Let me just write the equation again. We have solid X here, and this solid X is undergoing thermal decomposition, and then it gives us solid D, and this solid D is yellow when hot and white when cold. And then you also have another gas being obtained from the same thermal decomposition, and this gas is brown in color. Now, the only known brown gas in color is nitrogen 4 oxide gas. So they'll ask you to identify the identity, or to give the identity of this gas. Let's call it gas Y, the identity of gas Y. So gas Y will be nitrogen 4 oxide gas. And also, you give the identity of solid D. Now, the hint that will give you the identity of solid D is that it is yellow when hot and white when cold. The only solid which is yellow, it is zinc oxide. And now you will be asked to identify solid X. So a solid which when heat, we obtain zinc oxide and nitrogen 4 oxide. Which one is that? It's zinc nitrate, because it cannot be zinc carbonate. If it could be zinc carbonate, then they'll tell you that the gas, this gas, it turns lime water into white precipitate. That lime water is calcium hydroxide. So if it could be calcium carbonate, then they'll tell you that this gas turns calcium hydroxide into white precipitate. That's lime water into white precipitate. Then it could have been zinc carbonate. But in this case, because it's producing a brown gas, only nitrates can produce brown gas, because they contain nitrate, which is a compound of nitrogen 4 oxide gas. Good. Also, apart from zinc, you should also know that they can also question you about lead. If you also heat lead nitrate, you'll obtain lead oxide and nitrogen 4 oxide gas and water. You should also know the color of lead oxide. It's orange when hot, and yellow when cold. Orange when hot and yellow when cold. So apart from reacting copper with concentrated nitric acid, we can also obtain nitrogen 4 oxide by thermal decomposition of those metals which are below sodium in the reactivity series, just as we have shown above. Okay. So next, Our next subtopic, we are going to talk about ammonium gas. Ammonium gas. Ammonium gas. Now, ammonium, from the formula, it's a compound of nitrogen and hydrogen. So, in preparation of ammonium, we simply react nitrogen and hydrogen to obtain ammonia. So, like other or like most compounds, ammonium can also be prepared at laboratory level or at the industrial level. Now, at the laboratory level, to obtain ammonium, we simply react here. We have calcium hydroxide and ammonium chloride. So when we heat this, these ones, they should help us obtain So we have this gas X, and you know that we are preparing ammonium gas, so automatically gas X is ammonium gas. But there are a few things I want you to note here, because this question is very common, and when it's said, most students usually get it wrong because of just these few things that they don't understand. One, we are reacting calcium hydroxide. So to obtain ammonium, we simply react an alkali, a suitable alkali. And the most suitable alkali that we prefer in this experiment is calcium hydroxide. When we talk about an alkali, it's simply a soluble base. When we react this alkali with an ammonium salt, which in this case is ammonium chloride, we shall obtain this ammonium chloride reacting with calcium hydroxide. We shall obtain calcium chloride plus ammonium gas, and this is water. Now, if you see, if you check my experiment here, this one, it's not correctly drawn. It should be in this form. It should be in this form. So if you see my experiment here, this reaction, here you have calcium hydroxide, and you have ammonium chloride. Now, if you check my experiment, the setup, you realize that the flask is set in a sliding position. You will be asked to explain why the flask is set in a sliding position. Or in another diagram, they will draw it being set in an upright position, meaning that if it's an upright position, in this process, we are obtaining water here, and it's obtained as steam. And this water, it condenses on these cooler parts. So if it's in an upright position, then that steam will condense, and then it will flow back in the reaction chamber, which is the flask here, and then it will cause the flask to crack, simply crack. Also, this one is a drying agent. This is a drying agent, because you want to obtain ammonium when dry. And the preferred drying agent here is calcium oxide. This is calcium oxide, which you call quicklime. So quicklime, which is calcium oxide, is the most preferred drying agent used in this experiment. The reason why you don't use other drying agents like sulfuric acid and just anhydrous calcium chloride is because they will form compounds. For example, if we could have used concentrated sulfuric acid as a drying agent here, then this ammonium could have reacted with sulfuric acid to form ammonium sulfate. If we could have used sulfuric acid as a drying agent, it could react with ammonium to form ammonium sulfate. And if we use anhydrous calcium chloride to dry ammonium, if we use this to dry ammonium, then it will also form a complex. It will also form a complex compound. If we use ammonium to dry, if you use anhydrous calcium chloride to dry ammonium, it will form a complex compound, which is calcium chloride with form also of ammonia. So we shall not obtain the ammonium gas that we intended to obtain. That's why the most preferred drying agent is calcium oxide. Now, without wastage of time, before we talk about the laboratory preparation of ammonium gas, before we talk about the laboratory preparation of ammonium gas, let's talk about the actions of ammonium gas in oxygen. So when we heat ammonium in oxygen, we obtain two different equations. And these different equations, they depend on certain conditions. One, ammonium can react with oxygen in absence of a catalyst, just like this. We can have here oxygen. This is oxygen gas entering here. And then here we have a cotton wool. And then we can have ammonium gas here. This is ammonium gas entering here. and now this ammonium gas is being burned. Now, in this experiment, we are burning ammonium in absence of a catalyst. One observation is that we shall observe a green-yellow flame because ammonium gas burns with a green-yellow flame. So one observation in this experiment that shall observe a green-yellow flame because ammonium burns in air with a green-yellow flame. Now, this is the equation. When you burn ammonium in air, in absence of a catalyst, you shall obtain nitrogen gas and steam. But in another experiment, we can also burn ammonium gas in presence of air. So this one, it will give us 4 moles of nitrogen. 4 moles of nitrogen. So we have 2 nitrogens, We have oxygens here. How many moles of? We have 12 here. So you'll have 6, and then you shall have 3. So that's the balanced equation. When we burn ammonium in air in absence of a catalyst, this is what we obtain. But what if we burn ammonium in presence of a catalyst? So if we burn ammonium in air in presence of a catalyst, we shall obtain nitrogen 2 oxide plus steam. Now, I want you to note this. In presence of a catalyst, which in this experiment, the most preferred catalyst, you have the platinum catalyst or the platinum wire, or you can also use copper wire. So copper wire or platinum wire can be used as a catalyst in this experiment. So when we burn ammonium in presence of a catalyst in air, we obtain nitrogen 2 oxide and steam. Now, they'll ask you the observation in this experiment. While we were talking about nitrogen dioxide, we said that it's very unstable, and when exposed to air, it will be immediately oxidized into nitrogen dioxide. And nitrogen dioxide, we said that one of its physical property, it's a brown gas. So during this experiment, if you are asked then to identify one observation that shall be noted here, is that brown fumes of nitrogen dioxide will be formed. In other equations, or in other experiments, or other questions in examination, they'll ask you, using equations, explain the observation. Now they want you to explain that observation using equations. The first equation will be this. When ammonium reacts in air, in presence of a catalyst, it's obtained nitrogen 2 oxide, this nitrogen 2 oxide, and steam. Now, to observe those brown fumes, we say that nitrogen 2 is unstable, and it will be readily oxidized to obtain nitrogen 4, which will give us brown fumes. So the brown fumes obtained here are of nitrogen 4 oxide gas. So that's the observation made there. So you should know both equations because they come in examination. And to balance this one, we call it a 45-46 equation. You see, what differentiates an A student and a B plus student is those minute details that are in these concepts. So if you don't know this, you can spend a decade trying to balance this in examination room. And of course, by the end of that decade, you'll still get it wrong. So these minute details, you should keep them at your fingertips if you want to score that an A plane in chemistry. So the difference between this equation and this equation is here. The product here is nitrogen gas, and the product here is nitrogen dioxide gas. So in the next lesson, we shall be talking about how we can prepare ammonium in the industrial level, because this was the preparation at the laboratory level. So thank you for the class, and you're welcome.
Kaunti maarufu kwa kuzalisha maziwa na ukuzaji wa majani chai. Pia, serikali ya kaunti inawahimiza wakulima kukumbatia mitindo mingine ya kilimo kuzidisha mapato.
Kama kuna kikundi moja inafanya biashara ya kuuza kuku, hao pia tumewafadhili kuwafunza jinsi ya kuhandle zile kuku kwa sababu wanaleta kwa wingi.
Haya yote tunakuletea katika Boresha Kilimo, toleo la kaunti ya Bomet.
Elimu ni nguzo kubwa kwa ujenzi wa taifa.
Tunachimba hadi mizizi kukuletea yanayojiri.
So mimi naomba tu serikali yetu ya Mungu, jibarikiwe na Mungu, iweze kuteremsha bei ya mafuta.
Yanayokukumba tuna maizi, tunakutetea sisiri. Kwa kweli ni speciali tukikupambia makala ya mwanamke mwake. Utasema hupendi mizizi ya habari. Nami Caroline Kimoi.
Are you an aspiring media practitioner, a graduate, or you just want to advance your skills in television production? Then welcome to Kenyatta University, where education meets innovation. KUTV, the premier university television station in Kenya, is now offering short courses in TV studio, field technical operations, and video editing. Through these courses, you will acquire hands-on skills on camera operations, media production, lighting techniques, audio-visual editing, and sound and visual control, and how to operate key equipment in modern TV control room. Enroll today at KUTV and discover your full potential in cutting-edge TV broadcasting. Graduates of these courses will receive professional certificates. For more information, visit our offices at KUTV Studios or call us on 020-870-4252 or 020-870-4255 or SMS us on 0739-110-544. KUTV, a new experience.
From the hospital corridors, we bring you experts to discuss issues affecting your health, from diet to mental health. The familiar and the ignored are both put into perspective. We then dive into the environment and look at the effects of climate change and its solutions. Join me, Mutegi K. Martin, every Friday at 9 p.m. as we learn on how to better our health while taking care of our environment. Only on KUTV.
Access to knowledge, solution to unanswered questions.
Guidelines to pursuing your rights and repossessing your property, intellectual or material.
This and more only on Law Matters.
Maelfu na maelfu ya wahamiaji wakiwa na watoto kutoka nchi za Amerika ya Kati wanaendelea kuwasili kwenye mpaka kati ya Marekani na Mexico.
The folks are going. Thank you very, very much. I appreciate it. Thank you.
Ni habari kutoka pembe zote duniani.
Pepo pasi vuguvugu, pepo pani idea.
Tazidi ananyonya, hanyonyi vizuri, anakuwa hayuko comfortable.
Jeshi la Jamhuri ya Kidemokrasia ya Kongo linapambana na waasi wa ADF.
Kwa sasa wanatoa wito kwa mashirika, makampuni na vile vituo vya uchukuzi.
Mambo mengi yatakwenda kama yalivyopangwa.
Hapa ni kuna mmoja wa viongozi wa chama cha wavuvi katika eneo hili.
Zaidi tunajaribu kuwapa chanjo ili ina boost ama inanyanyua kinga ya mwili, hiyo inaweza kupelekea kupambana na virusi.
Ni dunia ni leo, Jumatatu mpaka Ijumaa, moja kwa moja kutoka VOA Swahili, Washington DC.
They are powerful and influential. They make decisions in politics, education, finance, agriculture, health, sports, and all aspects of human life. But the impact of their decisions falls on you, the common citizen. KUTV Primetime News Thursday. We ask bold questions and pursue answers to